This is sigma notation. It's a short way to write addition of a bunch of numbers. But how do these several symbols able to represent that many numbers? Let's take a closer look, shall we? That big symbol is a Greek letter called sigma. Here it tells us that the whole thing means summation. Meanwhile, I here is the summation index. It's an increasing sequence of integers showing the position of numbers, also called terms in the summation. It starts from the lower limit written here below sigma and ends at the upper limit written above. In this example, the index is from 1 to 7, but it can also start or ends with other numbers like so. But why do you want to start indexing not from 1? Well, it's because of this expression next to sigma called summation function. Actually, sigma notation can only represent addition of number sequence that has some pattern related to the index. And this relation is determined by that summation function. In this example, the terms are, well, the index, but it doesn't always the case. By playing with the summation function, we can have a summation of squares of integers, reciprocals of integers, or reciprocals of squares of integers. And by playing with the limits, we determine the first and the last term in the summation. Got it? Okay, to check our understanding, let's see some problems. This one is straightforward. Since the function is I, it's addition of the index integer sequence from lower limit, which is 1, to the upper limit, which is 4. Then we add them all and we have the answer. Next problem. From the function, we know that the terms are the square of their index, and the index starts from 3 and ends at 6. So in each term, we just take the square of the index, then add them all together, and voila. Okay, third problem. Well, first we have to identify the summation function. So inspect the terms and see that they are all reciprocals of the index. So it's 1 per I. Then we examine the lower and upper limits from the first and the last terms, and we get 2 and 6. So we know that it's the summation of 1 per I, where I is from 2 to 6. In solving the first two problems, we add the terms manually one by one. This wasn't a problem because, well, the summation were short. But if we face one having like hundreds of terms, we better have another way to deal with those things. Fortunately, many of those summations have formulas. Once we know the function and the limits, it's a matter of choosing formula and plugging numbers. But it's better to understand why those formulas and where do they come from. Let's start from the simplest one. This formula actually is just a definition of multiplication. Adding certain numbers of a certain constant term, say n numbers of a, we have n times a. And this sum is just that, addition of n terms where each term is a. Let's see this formula in action. Here we have summations of 53s, hence we have 50 times 3 which is 150. Alright, now let's see another formula. This one can be used to find the summation of integer sequence starting from 1 to any natural number n. Let's derive this one, shall we? Consider the sum and expand. Then, copy the equation and paste it below the original. After that, reverse the expansion of the copy and add the two summations term by term. Now see that this right hand side consists of only constant terms, so now we can use this first formula, and after dividing both sides by 2, we have it. Let's use it then in problem number 5. Solving this problem manually will be very long and tedious. Fortunately, now we have the shortcut. So, calling the formula, substituting n with 100, simplifying, and we get the answer. Now that we know what sigma notation means, why not also see their mathematical properties? So, here are 3 of them. We can split the summation somewhere in the middle of its index, so we can turn a sum into 2 where one continues the indexing of the other. And with this, we can generalize our first formula, so that now the index doesn't have to start from 1. To obtain it, we begin with a sum that starts from 1. Then we split it at m-1 and see that the last summation is the one whose formula we want, while the other two are sums of constants starting from 1 and can be solved using this formula 1 we've derived before. So, calling that formula, reorganizing, and simplifying, we get the formula for sum of constant terms with a more general index. If we have a constant in summation function, we can move it outside. So if we have a summation like this, that is the summation of even numbers, instead of doubling the index to calculate each terms and summing, we can sum the index first and then doubling, which is a lot easier. Also, using this property, we can have a formula for just this sum. How? Consider the sum. Take 2 outside, use second formula, multiply it with the 2, and we get the formula for summation of even numbers. If our summation function consists of addition or subtraction of 2 terms, we can separate the terms into 2 sums like this. With these third properties, we can get a formula for this summation of odd numbers. So we split the sum, use formulas we've derived before, and we get formula for summing sequence of odd numbers. So, to sum up, we've learned what this sigma notation means, 3 of its properties, and some of its formulas. That's it. Thank you very much for watching.